how this can lead to a cyclic sieving phenomenon. And well, this is based on work with several people. So the stuff about virtual crystals is in collaboration with Okado, who also gave a talk earlier in this conference, and Shimozono, and then Fourier Shimozono. And then this work about promotion and cyclic sieving is actually current work with Stefan Pfannerer from Vienna, and then my two students, Joseph Pappe and Mary Claire Simone. So we are hoping to put that on the archive soon. So let me give you some motivation of why we are interested in this. And the motivation really comes from invariant subspaces. And invariant subspaces actually go back to Uma Teller-Weil. They have a paper in 1932 where they studied quantum mechanical properties of molecules, and they were interested in when things are invariant under certain actions. So here, as yesterday, we are looking at tensor products of representations, and then we are interested in the dimension of these invariant subspaces. And in terms of crystals, it actually turns out that these dimensions are exactly the number of highest weight elements of weight 0 in the corresponding tensor product of crystals. So if these representations V1 up to Vn have crystals associated to them, then we are looking at the associated tensor products of crystals. And then how does this promotion action come in? Well, if you have a tensor product, you can look at the action of the symmetric group as n on this by just permuting the tensor positions. And this action also goes over to the invariant subspaces. And then it turns out that the action of the long cycle corresponds to the promotion action. And this was observed in 2016 by Bruce Westbury. Okay, so I will define the promotion for you later on, but this is sort of like the motivation. And then once we have the setup, then how does the cyclic sieving phenomena come in? Well, now you have the set of invariant elements in this tensor product. You have this promotion action, which I just mentioned corresponds to the action of the long cycle. And then there's actually also a polynomial associated to this in terms of what's called the energy function, which I will also define a little bit later. And so if you sum over all elements in this invariant subspace and then you weigh it with this energy function, that gives you a polynomial in Q, and this triple, so the set, this action, and this polynomial, they exhibit what's called a cyclic sieving phenomenon. So basically what the cyclic sieving phenomenon does, again, I will define it later, but if you look at cycles of this promotion, then the sizes of the cycles can be obtained by putting certain roots of unities into this polynomial. So that's what we will see later on. So now let me go into more detail. So let me first sort of show you explicitly what these invariant subspaces, or in this case, actually the highest weight elements of weight 0 in the crystals look like in various cases. So the first case I want to look at is just the crystal of type A1. Okay, so yesterday we saw the very simple crystals for type AR. So type A1, the crystal B box is basically just, so the vector representation just consists of two elements. In my notation, just a box with a 1 and a box with a 2, or you can think of it as spin up and spin down if you're more like in a physics setting. And then remember, our crystal has certain operators. So in our case, we have this operator which we label F1, that takes a 1 into a 2. So our crystal is really, really simple. But then yesterday we saw that we can take tensor products of crystals to make them more complicated. So now here I'm going to look at a 4-fold tensor product of this crystal. And we are interested in highest weight elements. So then again, from yesterday, remember what that means. In this setting, when we only have 1s and 2s, remember that this signature rule told us that we always have more. If you read from right to left, you always have to have weakly more 1s and 2s, or in terms of this bracketing rule, you have to be able to bracket every 2 with a 1. So in this case, this would be the bracketing. Here's another example. So here, the 2s are also bracketed with a 1. So therefore, these are both highest weight elements. Then we also have this condition that they should be of weight 0. And in this case of type A1, that just means that we have the same number of 1s as we have the number of 2s. So here we have 2 1s and 2 2s in both of these examples. Okay, so in this case, when n is 4, there are only 2 such elements in this tensor product, and these are the 2. And you can see that there's a very natural bijection of these 2 Dick paths. So what's a Dick path? Well, you just have your line y equal to 0, and at each step you can either go up or down, and you can never go below the line y is equal to 0. And you also want to start and end on the y-axis. So you can see, right, if I associate a 1 with an up step and a 2 with a down step, then this particular element would correspond to, well, again, if I read from right to left, up, up, down, down. And then this one would correspond to the Dick path, up, down, up, down. And this is true in general if you look at these highest weight elements of weight 0 for type A1, they will always correspond to Dick path of the given length. So that's like a simple example that I guess many of you would be familiar with. Here's another example. Yesterday, we also saw the crystal of type C. And remember, this is how it looks like. So in this case, so for the simple vector representation or vector crystal, again, every element is just a single box. And now the boxes are filled with the letters from 1 up to R, and also R bar up to 1 bar. And this is the graph. So these are the crystal operators, the Fi operators. And now again, we are going to look at tensor products of these, and we are interested in the highest weights of weight 0. And well, how can we achieve weight 0? So remember that a box with an I gave us an EI, a box with a I bar gave us a minus EI. So we can achieve something of weight 0 if they sort of cancel out. So if I take a tensor product of 2 such crystals, then one way of how I can get weight 0 would be if I have a 1 and a minus and a 1 bar, right? Because then I would get as weight E1 minus E1, so I get 0. And you can see that this particular element is of highest weight because again with our bracketing rule, right? So if I look at the 1, there's a 1 arrow coming out. If I look at the 1 bar, there's a 1 arrow coming in, and then with our signature rule, these 2 would again be bracketed. And then here I have given you another example where I take a 4-fold tensor product, and in this case I get 3 highest weight elements of weight 0. So here I have a 1 and a 2. And again, this is highest weight because the 2 will bracket with the 1. And then this 2 bar will bracket with the 2 and so on. So these are all of highest weight. They're also all of weight 0 because here you can see I have a 1 and a 1 bar, a 2 and a 2 bar. So the overall weight is equal to 0. And there's actually a nice natural bijection between these elements in our tensor product of the crystal and what are called oscillating tableaux. So what is an oscillating tableau? This will just be a sequence of partitions such that if I go from one partition to the next, I either add a box or I subtract a box. So here in this case, I start with weight 0. Then, so for this bijection, I have to read my tensor product again from right to left. So then if I look at the next thing that you get, if I add this 1, that means my weight is now 1. So that means I'm adding a box. And then if I look at my next letter, I get a 1 bar, which gives us again weight 0. So I'm removing a box. So the corresponding oscillating tableau will be empty, 1 box, empty. And then similarly in this case, so first I'm adding 1 box, which is this box. Then I'm adding a box in row 2, which gives us this partition. Then I'm subtracting a box in row 2, which gives us this partition. And then I'm subtracting a box again in row 1, which gives us this partition. So this gives us a natural bijection between these highest weight elements of weight 0 and oscillating tableau. Any questions so far? Well, just ask if you have questions. So I want to give you one last example of combinatorial objects that describe these highest weights of weight 0 in the various settings. So here I want to look at type BR, and then I want to look at the spin crystal. So yesterday we haven't talked about the spin crystal, but for type B2, it looks very simple. So the objects are just tuples, or here I've written them as columns of height 2. So the 2 just comes because we are looking at type B2. And they can either be plus or minus. So you can have plus plus, plus minus, minus plus, and minus minus. So those are the 4 states. And then the crystal element, the crystal operators do the following. So an F2 just changes the second element, an element in the second position from a plus to a minus. So it makes this plus into a minus. And then all the other operators, Fi, if you see, so in this case, it's just an F1. If you see a plus in position I and a minus in position I plus 1, it will just swap the 2. So it will swap a plus minus to a minus plus. Okay, so that's how this crystal looks like. And in this case, it turns out that the highest weight elements of weight 0 are in bijection with what are called fans of Dick path. So in this case, 2 fans of Dick path. So we've just seen what a Dick path is, right? You can just go up or down, and you have to end up on the y-axis. But a 2 fan is just a tuple of Dick path where one of them has to be below the other one. Okay, so how does that work in the setting? So here I have an element in my crystal of weight 0, and it's also highest weight. If I associate with the bottom line white, and then the top line green, I can do the same sort of association that I did before. So for me now, a plus is an up step and a minus is a down step. So then this bottom line would correspond to this white path, And then the green, so the top line would correspond to the green path, which is underneath. So let's look at this bottom example, which is a little bit more interesting because here the two paths don't actually, they're not the same. So this is again a highest weight element of weight 0, right? We have the same number of pluses and minuses, so that's why we have weight 0. And then using the signature rule, you can again check that it's highest weight. If I look at the bottom line and view it as a dick path, then I would go up, up, down, down, which is this white path. And here for the top line, I would do up, down, which is this green path. Okay, so the claim is that, so for type BR and the spin representation, the highest weights of weight 0 are in one-to-one correspondence with these R fans of dick path. So in general, if we do a BR, there would be R such dick path. Okay. So those are the objects that we are interested in. And now I want to tell you a little bit about virtual crystals. And let me tell you, before I go into the details, let me tell you a little bit about why we want to do this. So what we want to do eventually is actually associate these highest weight elements of weight 0, or these R fans of dick path, or the oscillating tableau, with certain diagrams, which are also called chord diagrams, where eventually the promotion operator on the crystals, which I'm going to define, will correspond to rotation on these chord diagrams. And the reason why I want to talk about these virtual crystals is because if you know how to do that in a certain case, so for example, if you know how to do it for type C, then using these embeddings, so in our case, we will embed type B into type C, then you can sort of use knowledge from what you do for type C and transfer that to the knowledge for type B. So that's why I'm going into this. So what do you need to define a virtual crystal? So you need an embedding of algebras. Okay, so I'm going to call the first algebra, let's say, X, and the second one Y, and you need some embedding of X into Y. And here's some typical example that is often presented. So suppose you want to sort of embed type CR into type A. And in fact, you want to embed CR into type A 2R minus 1. Okay, and here are the two dinking diagrams for the corresponding Lie algebras. Here's the dinking diagram for type C. Here's the dinking diagram for type A 2R minus 1. And I've sort of folded this dinking diagram, right? The one for type R, type A 2R minus 1. And the reason why I've drawn it this way is because for this embedding, I would like to associate the 1 and the 2R minus 1. I would sort of like to associate them and associate them both to the dinking node 1 for type C. And similarly, 2 and 2R minus 1, 2R minus 2 should be associated with the dinking node 2, and so on up to this point. And then the node R, so the middle node of our type A diagram, would be associated to the node R of type CR. Okay, so how would I describe this? This embedding? So I need, first of all, some map which tells me which nodes in one diagram are associated to the nodes in the other diagram. So here, a node I in type C, so for example 3, would be associated with the node 3 in type A and the node 2R minus 3. So that's why we have this. right? So this, a node I is sort of associated to two nodes in the type A diagram. And for R, we only associate one node to it. So that's why sigma R only has one element in the set. And to describe our embedding, we actually also need some multiplicity factors, which I call gamma. So in this particular example, gamma I is equal to 1 for all of these nodes, but gamma R, so the special node is equal to 2. And so once you have the setup, then in this case, so in this case of the embedding of C into type A, there is actually an embedding of the root and the weight lattice of these Lie algebras. And so a fundamental weight of type C can be mapped under this embedding to a sum of fundamental weights of type A, where you sum over all the things that are associated to the node, and you also multiply everything by this multiplicity. So for example, omega 1 of type C would be associated to omega 1 plus omega 2R minus 1 in type A. And omega R would be associated to 2 omega R in type A. So that's how this embedding works. And if you have such an embedding, then you can try to sort of lift that to the level of the crystals. So let me call by V hat the crystal of type Y, so the one that we are going to embed into. And the crystal operators that I associate to this V hat will be denoted by EI hat and FI hat. So this is also called the ambient crystal. And then I need to tell you what my virtual crystal operators are. So they are sort of, they mimic what happens up here with this embedding. So an EI operator is now a product of operators of my type Y crystal, of my V hat crystal. Okay, and you take the product of all the things that again are associated, the associated nodes in the linking diagram, and you also scale it with this factor. So again, so for this embedding of type C into type A, E1 would be E1 hat times E2 minus E2R minus 1 hat. One thing that you might ask is, well, which order should I use these operators in? But it turns out that when you do these embeddings, the operators that are sort of together always commute, so it doesn't actually matter in which order you write these products.
Hi, Anna, can I ask a question?
Yes, sure.
Why is it called virtual crystal? Is it not a real crystal in some sense?
Yeah, so it's not a real crystal because, I mean, it will turn out to be a real crystal, but the construction itself is not real because, as you can see, so in the V hat is a real crystal. It's a crystal of type A. But then the way that we construct these is we are actually taking products of crystals in this virtual crystal. So you're sort of skipping steps. And so if you drew the whole crystal, what you would do is you would be skipping certain error or skipping certain elements in there, because here, for example, in this embedding in type A, right, you would do an ER squared, so you would do an ER, but the vertex in the middle would be sort of dropped, and that's, I think, why it's called a virtual crystal. Does that answer your question?
But you said it will turn out to be a real crystal.
Yeah, so it will turn out to be isomorphic to a real crystal. Yes.
Okay, thanks.
Yes. And yeah, I'm going to give an example in a second, so I hope then it will become clearer, hopefully. But let me actually first give the sort of formal definition of the virtual crystal. So we have this ambient crystal. So in my example, it would be this crystal of type 2r-1. And then the virtual crystal is a subset of this, such that, so we always want this ambient crystal to be associated to a representation, or sometimes in the literature, you also see that there should be a Stembridge crystal. Then we want that the string length, if you look at elements that are sort of associated under this map sigma, the string length should be equal. So an epsilon I j hat should be equal to an epsilon j prime hat. And then also both of them should be multiples of this, this factor gamma that we had. And if you have that, you call these aligned. And if you have that, then you can also define sort of the string length of this virtual crystal by taking any representative j, because they are all the same. So you can take any representative j and you can also scale it by this factor. And that will turn out to be the string length in the virtual crystal. And then here's one more condition that you need, that so the subset that you've chosen is closed under these virtual crystal operators E and F. Okay, so let me give you an example, and then I hope I will also answer Lauren's question. So let's do this embedding again of type C2 into type A3. Okay, so my claim is that if I take as my ambient crystal now a tensor product of two things, so the crystal B box and the crystal B associated to a column of height 3. So in type A, the elements in here would just be semi-standard Young tableau of shape 1, 1, 1. So basically just increasing columns, strictly increasing columns of height 3. And then here is sort of my virtual crystal, right? So now what I do is I take the highest weight element in here, which would correspond to 1 tensor 1, 2, 3. My virtual crystal operators are these. So my F1 really corresponds to F1 times F1 hat times F3 hat. So if I want to now move in this virtual crystal, I really need to apply 2 crystal operators in the ambient crystal. And so this 1 makes this 1 into a 2, and the 3 makes this 3 into a 4. So this is what I meant, that you are skipping steps. So in the real crystal V hat, you would only do 1 crystal operator at a time, so you would have more vertices. But in this virtual one, you're skipping steps because you take products of these operators. And then the F2 is F2 hat squared, so then I have to take an F2 times F2, which makes these 2 2s into 3s, and so on. So you get this crystal, and then you can see that this crystal, or this virtual crystal, is actually isomorphic if you only, isomorphic in the sense that as a graph, where I label these blue and this red, as a graph, this looks isomorphic to this crystal. So in that sense, a virtual crystal actually models a real crystal. So I hope this answers Lauren's question.
Can I just ask a question as well, yes, before you go? I think I meant, because you talk about crystal, but I find it hard to understand what crystal doesn't.
Oh, sorry, it's very hard to hear you.
So you were talking about crystals that come from representations.
Yes.
So what is a crystal that doesn't come from a representation? I mean, what are you talking about representations of? I mean, because the only thing you've got really is the crystal action. And they're kind of always representations of that.
Yeah, so
I was missing something, sorry.
yes, so with the axioms that I gave yesterday, just for a Kashiwara crystal, there are crystals that I could draw that don't actually come from a representation. So I could give you one here. Sorry, my drawing won't be very good, but so for type A, for example, you could think of a crystal like this, which, so where this would be labeled, let's say 1, 2, 2, 1, 1, 2, 2, 1. And this crystal would be of type A, let's say A2, because it has 2 crystal operators, 1 and 2. It satisfies all the conditions, if I put the correct weights on it and so on, that I wrote down for the Kashiwara crystals yesterday. But it actually does not come from a representation. The crystal that would come from a representation would, for the adjoint of type A, would actually look like this. Actually has one more vertex. So here we would have 1, 2, 2, 1, 2, 1, 1, 2. And so I didn't go into details about this, but you can distinguish between these two by enforcing what are called the Septembre-Octobre axioms. So there are sort of 2 ways of how you can make sure that something comes from a representation. Either you actually start from a UQ of G representation and you take the limit as Q goes to 1, and you make sure that the combinatorial model that you have comes from that.
Do you mean Q is 0?
Yeah, Q, yeah, sorry,
yeah.
Q goes
Okay.
to 0. Yeah, sorry.
Okay.
It's very early in the morning here, so I need another coffee. Or you can sort of enforce these Septembre-Octobre axioms, which would not allow this to be a proper crystal. So the Septembre-Octobre axiom say that either you 2 crystal operators commute, or they sort of form these hexagon kind of parts of a graph. So I didn't go into details about this, but things that crystals that actually come from representations have to satisfy more conditions than what I gave yesterday.
Okay, that's very helpful. Thank you.
Mm-hmm. Yeah, any other questions? Yeah, and one thing that I wanted to mention is that yesterday we saw that you can take tensor products of crystals, and if you have a virtual crystal with these conditions that the things are aligned, then if you have 2 virtual crystals, you can also take a tensor product, and that tensor product will again be a virtual crystal. So that's very useful. So you can actually take tensor products of these crystals and have the same properties that you require for the input. Okay, so now I want to basically do this virtual crystal construction for this B spin crystal that we looked at. And the reason is that I sort of want to use knowledge for type C that is known for how to embed things into chord diagrams, and use this virtual crystal embedding to then use what is known for type C also for type B. And so here I have just drawn the crystal for type B3. So now we have these triplets where every entry can either be a plus or a minus. An F3 operator changes the top plus to a minus. So that's this rule. FR changes the top R plus to a minus. And then an FI operator, if you have a plus in position I, a minus in position I plus 1, it just flips those 2 things. Okay, so this will be the crystal of the spin crystal of type B3. And what I want to do now is give give you a formulation of that crystal as a virtual crystal. So what we will embed it into is a crystal of type CR. And in fact, we are going to embed it into an R-fold tensor product of the B box crystal. And so the set that will actually consist of our virtual crystal will be the component in this V hat of the component of the highest weight of the component that contains the highest weight R minus 1 down to 1. And it turns out that as a set, so the vertices will consist of all these tuples such that they are strictly decreasing. Where I use the following order, I use the order that 1 is smaller than 2 is smaller than R, and then R is smaller than R bar, and so on is smaller than 1 bar. Okay, so that is the set. And the virtual crystal operators, in this case, my sigma only consists of one element, so I corresponds to I, but we do have these multiplicity factors. So an Fi will correspond to an Fi squared in this ambient crystal, except for Fr. Fr just corresponds to Fr hat. And here is again sort of my real crystal coming from a representation, the B spin of type B3 as a virtual crystal. So as I said, we are now looking at a threefold tensor product. So I'm going to look at 3 to 1. And the F3 corresponded to the F3. So the F3 here, the F3 hat just makes a 3 into a 3 bar. And then the other crystal operators, you have to take squares of them. So here I have to take an F2 squared. So then F2 squared makes a 2 into a 2 bar, but it also makes, it makes a 2 into a 3, and it also makes a 3 bar into a 2 bar. And you can see that that sort of corresponds to switching a plus and a minus. So the bijective correspondence is really, if you see a plus here in position I, this will correspond to an unbarred letter here. If you see a minus in position I, you will see that letter as a barred letter. So here I have a minus in position 2, so I see a 2 bar. So that's an easy correspondence. But this is, my claim is that this is actually a virtual crystal embedding. So now that we know about these embeddings, now I'm actually going to tell you about what the promotion operator is. And this actually uses the crystal commuter that was introduced by Enriquez and Chemnitzer. And what this crystal commuter does is, if you have a tensor product of two crystals, it basically flips those two tensor factors. So it makes a B lambda tensor B mu into a B mu tensor B lambda. And the way that it does it is it uses what's called the Lustig involution. So the Lustig involution is just a map on a crystal itself, and you can think about it as just flipping the crystal upside down. So it maps a highest weight element, so the one where no arrow is coming in, to a lowest weight element where no arrow is coming out. And then sometimes you also it switches an Fi to an Ei prime. So it sort of flips the arrows around, and sometimes you have to relabel the arrows. But if we look back at our example here, right, here you could just flip the crystal upside down, and the label of the arrows would actually be the same, because this green arrow would map to this green arrow, this red arrow would map to this red arrow, and so on. But for type A, for example, an F1 would have to be mapped to an E n-1. So yeah, that's the Lustig involution. And then this crystal commuter flips the two tensor factors. So the BC goes to CB, but then it uses the Lustig involution to flip the crystal. And then it flips it again, flips the whole answer again. Okay, so that was introduced by Enriquez Chemnitzer, but we can use that now to define the promotion operator on our crystals. So if you have an n-fold tensor product of a crystal, what we are going to do is we are going to take this crystal commuter, and we are sort of splitting off the last tensor factor. So we have an n-fold tensor product. We are taking the first n-1, and we are splitting off the last one. So basically, what that means is you take your n crystals, n-1 crystals, and the last one, and you sort of flip that to the very end. And that is what's called the promotion operator on that crystal element. And here I have an example. So here I'm going to take again my type A1 crystal. Remember, those corresponded to the Dick path. Here is one element that we had, the 1, 1, 2, 2. And I now want to operate on that with my promotion operator. So I sort of split off the last factor, the last one. Then I'm going to take this piece, and it is a lowest weight element now. I'm going to make it into a highest weight element, which I've done here. So if you just flip that in your crystal, a 2 to 1 becomes a 1 to 1. I do the same for the single piece. So a 1 becomes a 2, and then I put them back together. So therefore the promotion operator on 2, 2, 1, 1, well, becomes, this was my front piece, it became this. So sorry, yeah, the front piece, it became this, and now it's sort of this back piece. And then this 1 here became this 2 here. So this is my promotion operator. And as you can see, it maps a highest weight element of weight 0 to another highest weight element of weight 0. Okay, so it is actually an action on the objects that we were interested in. And so the reason why, or basically what we want to achieve now for not just this simple case of type A, but basically the spin crystal, is we want to get some map from this invariant subspace to some sort of chord diagrams where the promotion action can be seen as just a rotation on these chord diagrams. And in type A, here's an example. Here I just wrote a standard tableau of a 2-row shape, and they're in bijection with these highest weight elements of weight 0 in type A1. So for example, here I have a 1 in row 1 that corresponds to this 1. I have my 2 in row 2, this corresponds to this 2. A 3 in row 1, this corresponds to this 1, and so on. So there's really a 1-to-1 correspondence between the standard Young tableau and my highest weight elements of weight 0, or the Dick path. There's a promotion on standard Young tableau, which I'm now not going to spell out, but basically what you do is you remove a 1, then you do jeu de taquin, and then you fill the empty box again with a letter, and you subtract 1 from all elements. So that's how you can define promotion on these standard Young tableau. And it turns out that that actually corresponds to the promotion on these crystal operators that I've just defined. But then there's also a map from these objects to these chord diagrams. And again, the map is relatively easy. So here I'm bracketing, if I do the crystal bracketing rule, right, I'm bracketing the 2 and the 1. So that's why in this chord diagram, the 1 and the 2 have a line between them. So the chord diagram is just the numbers from 1 up to, in this case, 6 on a circle. And I, because these were bracketed, I put a line, 3 and 4 are bracketed, so I put a line, 5 and 6 are bracketed, so I put a line. And then you can see that the promotion here really just corresponds to rotation on these diagrams. And here's another orbit under promotion. You can play the same game. So here I have, for example, this chord diagram, and then under this promotion action, it rotates things. Okay, so this is for the very simple case of type A1. And what the aim is, we want to basically now do something similar, but for the other types. Okay, and so for type AN-1 CN, for AN, the adjoint representation and the vector representation, and for CN, the vector representation, this was done in a paper by Fanera, Ruby, and Westbury. And so what I'm doing with my students, Joseph Pappe and Mary Clay Simone and Fanera, is that we basically use this virtual crystal embedding that I just defined, where we take our spin crystal of type Bn, we have embedded it into a vector, a tensor product of these vector representations of type Cn, and then we can use this construction to also find a map from these highest weight elements of weight 0 to certain chord diagrams, such that the promotion action corresponds to just rotation on the chord diagrams. Okay, so that's basically what this is saying. And I don't want to go into too many details of how this works, so I just want to give you a very brief outline of the construction, because if I did this in detail, I would have to introduce a lot more things. But basically what we are using are certain promotion evacuation diagrams that Lennart introduced. This part basically shows that promotion and rotation intertwine. And then we also use certain foamine growth diagrams to describe the promotion, and that basically shows injectivity. And then we are using this virtual crystal construction to embed everything from type B into type C, where the map to these chord diagrams is already known. Okay, so that's the basic outline. Any questions so far? Okay, so then in the last couple of minutes, what I want to do is show you how you can actually use this construction using the promotion operator to get certain cyclic sieving phenomena. So let me just first tell you what the cyclic sieving phenomenon is. So it was introduced by Reiner, Stanton, White, and what it says is the following. So suppose you have a finite set X, and you have a cyclic group acting on the set X. Then what you do is you take a root of unity. So if your cyclic group is of, if let's say of order n, then you take an nth root of unity. And then you also have a polynomial in Q. Then we say that XCF exhibits a cyclic sieving phenomenon if if you evaluate this polynomial at at this root of unity to the d, then this is precisely the size of the orbits of this of this promotion or the cyclic group action. Okay, so now what we want to do is we want to sort of take this to the setting that we just discussed. So we want to describe such a cyclic sieving phenomenon for the oscillating tableau. So this was type C. And then these R-fans of dick path, remember this was the spin representations for type BR. And the action that we want to use is this promotion action. And to describe the polynomial associated to this, I need to briefly define what I mean by the energy function. And the energy function is actually defined using what are called affine crystals. So far, I've only talked about sort of crystals associated to classical Lie algebras, but these affine crystals correspond to Kac-Moody Lie algebras. So you would have an extra crystal operator E0 and F0. And that is basically this zero operator is used to define the grading. So let me first introduce what's called the local energy function. So the local energy function can be defined recursively using these crystal operators. So it's constant on classical components. So if the I is not equal to 0, it doesn't change. So it's constant. And otherwise, it might change by plus or minus 1, depending on how my E0 operator acts. And just for concreteness, let me tell you what the answer is for type C. So the type C vector representation, but now affine, the crystal looks like this. So it looks the same as before, but we have an extra 0 arrow. And if you sort of unravel the whole definition that we had, then you can find that this local energy function is actually either 0 or 1, depending on whether A is less or equal to B, or whether A is bigger than B, in which case it's 1. So if you use this ordering, then this is sort of like you can think of that as a descent, right? If it's a descent, the local energy is 1. If it's not a descent, it's 0. For the spin representation, it's slightly more complicated. So you get another expression for this. It just counts sort of the number of minus signs in this left tensor product. But again, there's like an explicit formula for it. And then having the local energy, you can now define the energy function, which is basically an analog of the major index, right? So we saw in type C, this basically counts the descents, and then you are summing over the positions of the descents, which is really an analog of the major index in type C. And now we are going to define the polynomial as just the sum over all these highest weight elements of weight 0, and we are grading it with the energy function. And then the statement is that, well, if we look at these highest weight elements of weight 0, or equivalently the R-fans of dick path or oscillating tableau, we look at the promotion action, and this polynomial in terms of the energy function that actually exhibits a cyclic sieving phenomenon. And the proof uses various results in the literature. And I want to end by saying that instead of the energy function, we have a conjecture for another polynomial that we think also gives you a cyclic sieving phenomenon, which is basically a Q deformation of the number of R-fans. So this is only for the R-fans of dick path, this particular conjecture. So here's a Q deformation, simple Q deformation of the number of R-fans of dick path. And we are conjecturing that this also gives you a cyclic sieving phenomenon. But one thing that you observe is that the polynomials that we have, so the one in terms of the energy function and this other Q deformation of the R-fans of dict path are actually not the same, right? So here, for example, we have a Q to the 12, whereas we don't have that here. But if you take everything modulo Q to the 6 minus 1, the two polynomials are the same. And therefore, if you plug in 6th root of unity, then the polynomials are actually, I mean, under that substitution, they give you the same answer. Okay, thank you very much.
So the R times of dict path in violation with some like R triangulation.
Sorry, it was hard for me to understand. Can you repeat?
So the R times of dict paths, they are in violation with some kind of triangulation where like
Okay.
K crossing triangulation. So would the promotion be some kind of rotation of the
So if I understood correctly, you're saying the R-fans of dict path are in bijection with certain triangulations?
Yes, I don't remember exactly, but you know, the non-crossing partitions here.
Okay.
Crossing partitions, but at most R arcs can cross at the same time.
And do you have like a rotational symmetry on those?
Probably once you draw them, you can rotate.
Okay.
Yeah, send you an email.
Yeah. Okay. Yeah, that would be very helpful. Thank you.
So thank you once again.